So here's a fairly straightforward example where we're asked to determine whether a collection of vectors in R3 constitute a linearly independent set. Since this is the first example of our working with linear independence, I want to make sure that we base it on the definition. So vectors are linearly independent if the equation, let's say C1 times vector 1, in this case that's, well, I'm already writing it wrong. Okay, 1, negative 2, 3, plus C2 times vector 2, in this case negative 1, 0, 2, plus C3 times vector 3 equals the 0 vector. And here we've got a homogeneous equation. So the vectors are linearly independent if this system has only the trivial solution. And the trivial solution refers to setting all of the scalars equal to 0. If that's the only way to generate the 0 vector as a linear combination of these vectors, then we say that the vectors are linearly independent. The trivial solution is kind of a cheap solution where, okay, sure, if somebody challenged us to make 0 out of these vectors, the cheap way to do that would be 0 times this vector, 0 times this vector, 0 times this vector, done. The question is whether there is a more interesting solution, which we call a non-trivial solution. So to determine that, we could set up an augmented matrix, same old story. I got a vector equation here that's equivalent to an augmented matrix, or it could be represented as an augmented matrix with these vectors as the columns. And then that would be augmented with the 0 vector over here. And now we row reduce this thing and see what the solution set looks like. So we could do 2 times row 1 plus row 2. That'll get us a 0 in this entry here. My matrix gets sloppier with every step. Okay, because this would be 2 plus negative 2. And then this would be negative 2 plus 0. 2 times this. So 4 plus 1 and 0 plus 0. All right, I want to also go ahead and get a 0 in this position here. So to do that, we could do negative 3 row 1 plus row 3, because that will give me negative 3 plus 3. And then negative 3 times this will be positive 3 plus 2. Negative 3 times this would be negative 6 plus 1. And then 0 plus 0. Right, let's just double check here. Because you know the worst thing is when you do some tiny arithmetic error and then everything goes haywire. Okay, looks like we're good. So next thing is, well, I have a pivot here. I have a pivot here. I would now want to get a 0 in this position. So this is looking like it might get a little messy. Row 3 looks like the friendly column, or the friendly row here. So I'm going to continue to work with row 3 and say, okay, let me do 1/5 times row 3 and then see what I can do here. So I don't really want to do negative 1/2 times row 2 right now. I'm just seeing if I can avoid that. So 1/5 times row 3 will give me 0, 1, negative 1, 0 in row 3. And then I'm going to swap. Might seem like the wimpy way to approach this, but if you're doing different row operations, that's fine. You know, as long as you're using those legal elementary row operations, you may end up with a different echelon form, but our conclusion should be the same. So I did maybe a couple extra steps that didn't necessarily need to be done, but it makes the arithmetic more straightforward. So now if I want to get a 0 in this position right here, I can just do 2 times row 2 plus row 3. So that will be 0 plus 0, 2 plus negative 2, negative 2 plus 5, right? Negative 2 plus 5 here, and then 0 plus 0. Now, this thing is now in echelon form. You could reduce it further if you want to get it all the way to the reduced echelon form, but you don't have to. Let me point out that, okay, we now have a pivot in every column. So that's definitely noteworthy. Let me say first, okay, so suppose we're moving along trying to solve the system. So what you might do next is for row 3, write 3 times x3 equals 0. Well, only way that's true is if x3 equals 0. Okay, so we've established that x3 has to equal 0. Moving up to row 2. So this thing says 0x1 plus x2 minus x3 equals 0, but we just said that x3 is 0. So this is actually x2 minus 0 equals 0. Well, then x2 has to equal 0. Moving up to row 1, which let me just write it over here. So this row 1 right here, way over here, tells us that x1 minus x2 plus 2 times x3 equals 0. But now if we plug in what we already know, which I'm trying to scroll down here, it's not letting me. Okay, well if we plug in what we know, we have x1 minus x2, which is 0, plus 2 times x3, which is also 0, equals 0. That's not 20, that's 2 times 0. So x1 equals 0. Okay, well then if we're saying that x1, x2, x3 all have to equal 0, oh, and I should have been using C1, C2, C3, sorry guys. But so that means we're talking about, yes, all we have is the trivial solution. And if we only have the trivial solution, then the vectors are linearly independent. Now, let's generalize this a little further. So I was pointing out we have a pivot in every column. When you have a pivot in every column like this, that tells you there are no free variables, which tells you this system has only a single solution. Remember that a linear system always has either 0 solutions, single solution, or infinitely many. So as soon as you see there are no free variables, then we can rule out infinitely many solutions. We can also rule out this ever being inconsistent. I mean, for one thing, a homogeneous system is always consistent. It's always got at least the trivial solution. So if it's got a single solution, then in terms of a homogeneous equation, we're talking about only the trivial solution. And if you only have the trivial solution, then the vectors are linearly independent. So to shorten this whole process, or at least to shorten the reasoning quite a bit, we can say that whenever you set up a matrix like this, you put a pivot, or you put the vectors as your columns, vector 1, vector 2, vector 3. If you end up with a pivot in every column, then the vectors are linearly independent. And you don't actually even need to write this 0 column on the back, because when you have a column of zeros, it's just going to stay a column of zeros. There's nothing interesting happening in that last column. So in the future, you can just set up a matrix with your vectors as the columns, vector 1, vector 2, vector 3. If you end up with a pivot in every column, then the vectors are linearly independent. If you end up with a non-pivot column anywhere, then remember, non-pivot column tells you there is a free variable, which means there are infinitely many solutions. So we'll definitely have non-trivial solutions. So the whole issue is if there is a pivot in every column, then the vectors are linearly independent. I'm using capital L, capital I for linearly independent. If there is any non-pivot column, then the vectors are linearly dependent. And that's going to be your short way to determine linear independence of vectors.